Hello again. This is Math 2134 coming to you from the College of DuPage. The title of this lecture is Relative Extrema for Multivariable Functions. And as always, I encourage you to be an active learner as you watch this video. Our objectives are we're going to find the relative extrema, that is maxes and mins, of a function of two variables, and we're going to solve some word problems where we're finding the maximum or minimum value for a function of two variables. Let's begin by talking about what does it mean to be the maximum or minimum values. Well, it means very much the same thing. For a function of two variables, it has a relative maximum at the ordered pair AB if f of AB is bigger than or equal to f of xy for all points xy in a region that really means a circle containing the point AB. And similarly, it has a relative minimum at AB if f of xy is bigger than or equal to f of AB for all points xy in a region that means a circle containing AB. Here's some pictures that will help us understand that. Here is a relative max. You see at this point, AB, the function is bigger than anything that is near AB. Similarly, here you see at AB, the function value is smaller than any value of xy that is near AB. And here, I'm not showing in the xy plane, but here is a relative and absolute maximum. That means it's relative to everything nearby, but it's also the biggest. This is just a relative maximum because it's bigger than anything nearby within a circle. And here is a relative and absolute minimum because it can be, it's less than anything in a circle around this, but it's also the lowest value that we have. So again, the definitions of relative and absolute max and min are the same as what we had before. But we do have an additional kind of thing that's happening. Over here, for example, you see at a relative maximum, this derivative and this derivative, but now their partial derivatives have to be 0. And here, for a relative minimum, this derivative and this derivative have to be 0. Again, they are partial derivatives. And the same thing is true over here. But here, what we have is both these derivatives are 0. This one's derivative is 0, and this one's derivative is 0 because they're both flat. Now this picture looks like a saddle, and you see that what I really have is, in terms of the x, I have a minimum, and in terms of the y, I have a maximum value. So this is called a saddle point, and we'll see more about that later, and we have to watch out for this. We have to understand how to find these values and how to test to make sure we know whether it's relative max, relative min, or a saddle point. And we do that using a test called the D test, the capital D test. So let f be a differentiable function of x and y. That means the partial derivatives exist. And let AB represent a solution to the system of equations. And this is the partial with respect to x is equal to 0, and the partial with respect to y is equal to 0. Now these are actually critical points, as we talked about earlier. These are candidate values. The AB, the solutions to these, are candidates for being a max or a min, but then we have to test. And the way we test is we look at an expression that we call capital D. So capital D is going to be the product of the second partial with respect to x times the second partial with respect to y evaluated at AB, and I subtract off the cross partial fxy at AB squared. So that is what D is, and you should commit this to memory. And then we have outcomes. Now if D is greater than 0 and fxx at AB is less than 0, it follows that f has a relative maximum at AB. If D is greater than 0 and fxx is greater than 0, it follows that f has a relative minimum at AB. Now if d is less than 0, it follows that it has neither a max nor a min at AB, and that means that there's a saddle point. And if d is equal to 0, the test cannot be applied. Now this is somewhat analogous to the second derivative test that we studied earlier before the midterm for functions of one variable. And again, you should review that. Saddle points are analogous to critical values at which the concavity changes and there are no relative maximum or minimum values. But in three-dimensional space, this is what it's showing you. So one of them turns out to be a maximum, the other one turns out to be a minimum. Relative extrema may or may not be absolute extrema. Testing for absolute extrema can be complicated. We will restrict our attention to finding relative extrema in this section and in most of the applications we consider. Relative extrema turn out to be absolute as well, often in many applications, most of the applications that we will consider, certainly. So, examples are worth 1,000 words, so here we go. Find the relative maximum and minimum values of this. F of xy equals x squared plus xy plus 2y squared minus 7y. So first thing we do is we must find the first and all the second order partials. You should make sure that you understand and can follow all these calculations. So fx is equal to this. Fy is equal to this. Fxx is equal to this. Fyy is equal to this. And the cross partial, Fxy, is equal to 1. So now we're going to solve the system of equations. This is to find the critical points where this one is equal to 0 and this one is equal to 0. So I'm going to take this and set it equal to 0. I'm going to take this one and set it equal to 0. Now I have two equations and two unknowns. You remember how to solve those, and you must be able to solve those. So we're doing this by substitution. So what we're doing is we're solving for x here. X is equal to minus 4y. So we substitute that into the first equation, and we found out that y is minus 1. So to find x when y is equal to minus 1, we substitute minus 1 for y in the original, or in this equation. To find it, we get x is 4. So that means that 4 minus 1 is the only critical point. So we'll evaluate f of 4 minus 1 as our candidate for the maximum or minimum value. And to check to see whether this is a maximum or a minimum value, we will substitute that into our expression for d. So this is fxx evaluated at 4 minus 1 times fyy evaluated at 4 minus 1 minus the cross partial squared. We substitute all our values in and we get 7. That means it is greater than 0, and the second derivative is equal to 2. So we have that d is bigger than 0 and fxx is evaluated at the critical point is bigger than 0. So it follows that this is a relative minimum, and the minimum value we find by substituting 4 minus 1 into our original function. We do that and we get minus 14. So here in fact it's a graph. So we found that the minimum is minus 14, and it happens when x is 4 and y is minus 1. That's the relative minimum. This talks about an example of a saddle point where you're stretching the cloth this way, stretching it this way as tight as you can, and it turns out that is giving you a tent roof of maximum strength. So a saddle point, and the tighter the curvature, the better it is. That is sort of an engineering application of saddle points. Let's do another example. We want to find the relative maximum and minimum values of this expression. Now notice here we have f of xy is xy minus x cubed minus y squared. So again, we proceed to find the critical points. So we take the first partials and the second partials, all of them. The 3 second partials and the 2 first partials. We get this, and this. Make sure you follow and can replicate these instructions, because this is the kind of problem I might ask you. And then we have to find the critical points, and in this case we're solving a system of equations. F sub x equals 0, x sub y equal f sub y equal to 0. So this is equal to 0, this is equal to 0. Again, we're going to solve for y, and so we get that y is equal to 3x squared, so I can substitute 3x squared for y in equation 5. I do that, and I get this expression, which I can factor. Factor the x out, and I find that x is equal to 0, or the other factor is equal to 0, meaning x is equal to 1/6. So you see I have two possibilities here. Now when x is equal to 0, I substitute back into this equation. I find out that y is equal to 0. So 0, 0 is a critical point, and f 0, 0 is a possible extremum. To find another candidate, we substitute 1/6 for x in equation 4 over here, and we solve, and we get y is equal to 1 over 12. So 1 over 6, 1 over 12 is another critical point, and this is another possible extremum. So we're going to use the d-test to check both of these to see whether they're a maximum, minimum, or something else. So for 0, 0, we substitute in, and we find out that d is equal to this. Substituting the values is equal to -1. Since that's less than 0, it says that's neither a maximum nor a minimum, it's a saddle point. For this one, when we substitute into d, we get 1, thus d is 1, and fxx evaluated, that is -1. So it follows that f has a relative maximum at 1/6, 1/12, and the maximum value is 1 over 412 by substituting it. Here's a picture. You see that that's a saddle point, and that is a relative maximum. Make sure you can do problems of this kind, and the first step is making sure you follow all these calculations. Let's do a word problem. So you have this company that produces two types of golf balls. One type sells for $3 each, and the other sells for $2 each. So the total revenue in thousands of dollars from the sale of X thousand $3 balls and Y thousand $2 balls is given by R of XY equal 3X plus 2Y. And the company also determines that the total cost of making these things, of producing X thousand of the $3 balls and Y thousand of the $2 balls, is given by this expression. How many golf balls of each type must be produced and sold to maximize the company's profit? Well, first thing is the profit is going to be the difference between the revenue and the cost. So it is this expression minus the whole of this expression. And that's a mistake many students will make. So you have to remember that you minus the whole of this expression. And then you simplify, and now we have an expression for the profit if we make X and Y 1,000 balls of the $3 and $2 variety. So now what we have to do is we're maximizing this, or trying to figure out what we get. So we take the first partials and the 3 second partials for this function. We get these values. Make sure that you see where all of this comes from. Now we have to find the critical values. That's going to be setting the first derivative equal to 0 in each case, and solving this simultaneously. And again, that's another effort that you have to do. Now here, what we really can do is just add the equations top to bottom, and the y's will cancel out. So we get minus 2x plus 8 is equal to 0, so x is equal to 4. And to find out what y is when x is 4, we substitute 4 for x in the equation, either 6 or 7, these equations. We get that y is 2. So x4, y is 2 is the only critical point, and it's a candidate to be the max or min. Now we will check to see what it is. So we're going to substitute this into our d, getting these numbers, and we get 4. So this is 4, and pxx at 4, 2 is minus 4. So since the d is bigger than 0 and the second derivative with respect to x is less than 0, at that point it follows that p has a relative maximum at 4, 2. Therefore, to maximize profit, the company must produce and sell 4,000 of the $3 golf balls and 2,000 of the $2 golf balls. And the maximum profit will be, and you'll plug this into your original equation for the profit, which is up here, and do the calculation, and we'll get $13,000. Now, sometimes we have constrained optimization, and like we did before, what we're going to do is we're going to eliminate variables to move it into a problem with fewer variables. So let's consider the following example of optimization with constraints. So a shipping company requires that the sum of the length, width, and height of a rectangular shipping box must be 90 inches. What's the maximum volume of such a box? And you see you can get different values depending on what you do. So we're going to let x, y, and z be the length, width, and height of the box in inches. And the volume of the box then is given by the function of 3 variables. The volume, as a function of x, y, and z, is length times width times height, or in this case it is x times y times z. Now we go up here and see that the sum of the box's length and width and height is 90. So that means I can solve for z in terms of the other 2 variables, and z is equal to 90 minus x minus y. So we can substitute that into our expression for z, and we get that v, but now you see there is no z, so we substitute in, and we get that v of xy is this expression. So that's the thing we're trying to maximize. So to find the critical values, what we're going to do is take the first partials and all 3 of the second partials. Again, you should make sure that you can do all of these calculations. And then we're going to solve the system for Vx equals 0, Vy is equal to 0, getting this. Now, since these are measurements, we can assume that all are positive, and that allows us to simplify the equations by dividing both sides by y, which is a positive number, and both sides in equation 9, so we get this after we divide this equation all the way through by y, and this one we divide all the way through by x, so we get this. So it's kind of a tricky way to approach it. So solving for this, we're going to get, and we will solve for one in terms of the other, we get y is equal to 90 minus 2x, and we'll substitute into the other equation here. We'll find that x is equal to 90 over 3, or 30. So you see, we know that x is 30. Now to find out y, we back substitute into either one of those equations, and we find that y is 30. And then z was 90 minus x minus y, so that means that z is 30 as well. Now we can test this critical point, and we look at d, and we find out that d is going to be positive, and that means that it is a minimum. Or excuse me, that means that it is it's the maximum volume. It's the maximum, and the maximum volume is 30 times 30 times 30. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.